Okay, last video for chapter 7 is to help you understand transition temperature, abbreviated T subscript M. So these kind of graphs are measuring how much heat a membrane can absorb before it turns into liquid, or before it transitions to its phase. Okay, so here the TM is 28 degrees. This is where the membrane is most stable, it's fluid, it has the properties of the fluid mosaic model. As you decrease the temperature, it gets more into a gel state, so things are harder to move. So think about, when you have really cold Jell-O coming out of the fridge, it's hard to move things around in there. Okay. Then you have, well, we don't really do this with Jell-O, but you can warm it up a little bit, and maybe the fruit you've embedded in the Jell-O can start to move around. But if you heat your Jell-O up too much, then it's going to turn to a liquid mess. Right? So we don't want our membranes to be a liquid mess, and we don't want them to be so tight that things can't move. So we want them at this nice fluid mosaic model temperature. Right, and this is just trying to show you in a different graph this phase transition, which is happening at the TM. Okay, so we're going from a liquid to, from a gel to a liquid. So tightly packed to lots of space. So as you change the composition of a membrane, you change its transition temperature. So here's a blank graph, and I'm going to just draw a membrane. And when I ask you to draw these, they're not precise. They're really just looking at peaks in, or peaks relative to one another. So I'm going to make my first membrane right there. So this is my standard membrane. And I'm just going to say it has fatty acids that are 18O, which means they have 18 carbons in the tail and no carbon-carbon double bonds. Okay. So, and unfortunately I have been struggling to change my ink colors with this. Okay, anyways, I will use some dotted lines. How about that? So if we changed our membrane, now our membrane is 18-1, which means now it has one carbon-carbon double bond. If you look back at figure 713 in your textbook, you will see that adding a double bond drastically reduces the transition temperature. So now my membrane has a much lower TM compared to the standard that I started with. Okay. Remember, the double bonds put kinks in the fatty acid chains, which makes it not pack as tight. Okay. So the membrane actually cannot absorb as much temperature, heat, before it turns liquidy. Okay. If we changed our membrane to a, say, 16O fatty acid composition. So we've got shorter chains, but no double bonds. really bummed that I cannot change my color. Pointer options. Oh, I might be able to. Ink color, blue. Woo. Oh, yay. Okay, figured it out. Okay, so here is our 16 and O diagram. So we've shifted the temperature a little bit. Not a lot compared to when we introduced that carbon-carbon double bond. Okay, so I'm not going to ask you for exact how many degrees did it change by, but drawing these relative to one another so that I know that you know how different types of molecules affect the transition temperature. Okay. Taking another blank transition temperature graph, one of the things I thought was the coolest from this chapter is learning about these Poikilotherms. And I don't know if I'm really saying that right, but that's kind of how it looks like. Okay, so these are our cold-blooded animals we like to think about, or even single-celled animals, protozoa or single-celled prokaryotes like bacteria that cannot regulate their internal temperature. Okay, sometimes I think I'm cold-blooded because I'm always cold, but all right. So they have to regulate the composition of their membrane based on the environment. Okay, so in order to not get too fluidy, not get too gel-like, they have to be able to change the composition, the types of lipids, the amount of cholesterol, things like that, or other sterols in their membranes. Okay. So let's just draw two graphs. And again, this is not for accuracy. This is just saying this is a greater TM. This is a lower TM. Okay. So this is in the cold, and this is where it's warm. Right? So one of the things I want you to think about is what would an organism have to do if it was going from one situation to another. Okay. So for instance, if it was going from a cold environment to a warm environment, right? So now if it kept its membrane as it is, it might get too liquidy, right? It's above the TM. So to keep your fluid mosaic state, one of the things it could do is it could decrease the number of carbon-carbon bonds. Carbon-carbon double bonds, right? Because more carbon-carbon double bonds puts more kinks, makes you have a lower transition temperature. It could increase the number of carbons in the fatty acid chain. So maybe go from 16 to 18, right? That's also going to help stabilize. It could also, what would it do with cholesterol? Let's think. So in the cold, cholesterol helps keep it from gelling, and in the warm, cholesterol helps keep it from getting too liquidy. So I think we would increase the cholesterol as we're increasing the temperature. This always hurts my brain. Right? So we're making our, as we heat up, we need to stabilize that cholesterol. Okay. Warm to cold. We would do the opposite, though more cholesterol would keep it from getting too thick. Cholesterol is always a weird one, right? So think about those. You'll have some questions on your homework to work through, and those are my videos for Chapter 7. Thanks.